Okay, thank you everybody for joining. I'll hand over to.
Yeah. Hello. So it is my great pleasure to introduce the speaker of the hijack today. So Doug Lin. Doug finished his bachelor's thesis back to a very long time ago in McMaster in Canada. So after that, he crossed the Atlantic to go to Cambridge to pursue the PhD. Shortly after that, he did a short postdoc in Harvard and Cambridge and start as a faculty member of University of California, Santa Cruz in 1979, which is like almost 20 years before I was born. And since then, I spent most of the time there. So Doug has been known for many things. So among his honors, I just want to mention, so he's member of the American Academy of Science and Art, and he received the Bruce Medal in 2015 for his lifelong contribution to astrophysics. And I think the most important title I want to mention is, as he suggests himself, he's a collaborator of the students. So he has a long history of pursuing international collaboration between all of the countries. And regarding this, one of his titles is maybe the founding director of the Kavli Institute in Peking University, which like cultivates a generation of young scientists from China. Some of them are sitting inside the audience. Doug is, probably the most, one of the most, if not the most, so influential theoretical astrophysics in planet formation field. So he has a lot of contribution which revolution our understanding of planet-to-star interaction, proto-magnetic evolution, and also like gas giant formation. And he has a broad enough science interest beyond that. So on stellar formation, so galactic dynamics, AGN physics, gravitational wave source. So as the title suggests, so stellar evolution, gravitational wave events, growth of supermassive black holes in AGNs. So we will learn more about that, and the floor is yours, Doug, please.
Thank you. Thank you. It's my great honor to be here. And in fact, I have been in this room maybe more than 10 years ago. So my recent interest has revived since 2015 in the context of AGNs and black holes. This subject goes back a long way, and ever since the discovery of quasars in the 1960s and the suggestion of Donald Lindenbelt that the powerful engine in the center of these systems is an accretion disk. And these concepts have been explored and studied in detail. And near home, this set of observations on the closest supermassive black hole is in the galactic center. And for this work, Nobel Prize have been awarded. When you look at the orbit of these young stars are all less than 10 million years old, and you can see there's distinctive this shape, and in the center there's also a group of S stars with highly eccentric and isotropic velocity dispersion. So if you try to draw analogy for folks who are interested in planetary system and the galactic center, you'll see there are many similarities, such as the mass of the central black hole versus the mass of these stars are similar to that of planets versus their host stars. And the period in the context of these stars range from decades to centuries, and here in the context of planetary system is in the same range. And the radius to semi-major axis ratio is also very similar, and if you infer back to some conditions that's needed to form these disks, and versus that powers AGN, you will also find great deal of similarity, including that the disk mass to the central object's mass is about a few percent, and their aspect ratio is about a few percent, and their gravitational stability parameter is almost in similar ranges. And protostellar disk persists to 3 to 10 million years, whereas these AGN disks could range from a few million years to 100 million years. So there's tremendous amount of similarity, and that can motivate one to develop very interesting analysis and try to study this system and not only stars interaction in this neighborhood of the disk, but also pay detailed attention on stellar population, S stars, and disk stars. And here are the old, we're just starting to pick up these very old stars, and which are low mass and have been here for a while. So these are probably the stars up here, and then these other stars are here. So I'm going to introduce to you today is the result of our recent investigation. Many aspects of what I will talk about is out-of-the-box thinking, and is actually very non-conventional. So to begin with, let's always base theory on observation. And now we have thousands, tens of thousands of these AGNs to play with and obtain from Sloan Digital Survey, and soon will be substantially enhanced by Roman and by others telescope. And we can start to develop these luminosity functions as a function of redshift. There's clearly an evolution, and which gives you some indication about an accretion rate. And also then you can start to look at multi-wavelengths measurements, and you get a bolometric luminosity. And if you know the mass of the black hole, and you can determine things like the Eddington parameter, and which is a parameter that you can accrete such that the Eddington limit is reached for a given mass. And this is typically of order unity. And the efficiency factor, which is the factor that you use to convert rest mass energy into radiation. And you can also persist to look at these evolution of the mass spectra as function of Z, and you can get very interesting results, and that infers for you a accretion rate for supermassive black hole. Here is measured in 10 to the 8 solar masses, roughly about 1 or 2 solar mass per year. And if their mass is lower, and they will scale accordingly. The conventional theory for accretion disk is that due to Shakro and Soniev and the so-called alpha disk model, where you use this turbulent viscosity with a unknown fudge factor, alpha. And now once you know this, this value of m dot as a function of m, you can actually work out from the conventional accretion disk theory that the interrelationship between alpha aspect ratio and the gravitational stability parameter, and you can describe into something very simple. But we're going to move away from that conventional theory. So using that conventional theory, very quickly you will find that in the region outside 100 or so gravitational radius, the disk becomes so massive it cannot support its own weight. So gravitational instability sets in outside about 100 or so Rg. Now, if you go to all the way out to about a few thousand Rg, you get into the region of the broad line region, and where you see characteristic spectral features which have a velocity width of order a few thousand kilometers per second. And still further out, there is this so-called dusty torus. So from the examination of reverberation map, reverberation map is a phenomena when the central source light goes up and down, and the light will shine on different parts of the disk, and then it will brighten up, and with some time delay. So this is like a time echo, And we can determine things by modeling, following, monitoring this kind of light path. We can determine aspect ratio for accretion disk, which is of order 10 to the minus 2. But we also know when gravitational instability sets in that the generation of the spiral density wave provides a very strong torque and which can transfer angular momentum, give you equivalent of alpha equals to 1. So now, here's when the story begins. So if you just use the conventional accretion disk, and then all this region becomes so unstable, the Q value becomes so small, and it will be globally unstable. And so one possibility is that in this region that maybe gravitational fragmentation would take place, and these are study simulations done for appropriate radiation pressure, dominant regime, and with appropriate cooling function, and the simulation seems to generate these fragments. So the proposition I'm going to make to you is that the outer part of the disk is heated by these embedded stars. That the stars form in this environment, and they continue to grow in this environment because the density of this disk is something like 6 to 10 orders of magnitude larger than the densest molecular core. So, and they don't move away. The stars that's formed in this region does not move. They do not move away from this environment. So they continue to accrete and grow, and they generate nuclear luminosity and to heat the disk. This is very unconventional compared to standard accretion disk model. Standard accretion disk model tells you that it is a viscous dissipation that heats the disk. Here we're talking about the embedded star that takes place. So now let's study details, okay? And that's just a proposition. So if you're embedded in this disk, and how they can accrete, this is a problem long ago due to Bundy-Hoyle-Littleton. And but in recent times, as we study planet formation, we realize that in this disk environment, when the disk flows, there's also limited by the Hughes radius, so we can actually determine the accretion rate taking these two effects into account. But this is not alone because when the star becomes very massive, it produces enormous amount of radiation, and it starts to reach the Eddington limit. And when you reach the Eddington limit, then you will slow down, and the accretion rate will reduce. In the context of a black hole, this limits the black hole growth to what is called the saltpeter timescale. And that timescale is long, but for stars, this timescale can be much shorter. And basically, here's a simulation Yishan Chen has done that as you reach the Eddington limit, you have radiation pressure that's exerting on the inflowing flow, and in this region, you have both outflow and inflow, and you self-regulate, and that reduces the accretion rate, limits the accretion rate. Now, if this process can occur, you can accrete material. If this material can reach all the way into the deep interior of the stars, then what happens is that you will supply fresh supply of hydrogen into the deep interior. And this fresh supply of hydrogen will be compensated by some mass loss, because when it reaches the Eddington limit, and then radiation pressure becomes so strong, some material will go out, and so you have basically metabolism, you have accretion and wind. And if you can balance this with material that can go all the way down to the interior, you'll indefinitely prolong the main sequence lifespan of the star. And for these stars, we refer to as immortal stars. And their mass can exceed 200 or 300 solar masses. However, most of these massive stars, if they're in isolation, very often that the core is insulated from the envelope by a radiative layer. And that radiative layer prevents the very efficient mixing, so the core's hydrogen content can get exhausted, and you start to evolve off the main sequence, and then you produce what is called the metamorphic star, transition from main sequence to post-main sequence. The difference in this context from the standard stellar evolution is that these stars are maintained at the Eddington limit for the mass and the helium content in their interior, because the helium content can play a major role, as I will show you. So here is a stellar evolution track and time scale, and here's the mass and initial ramp up. Here is the immortal stars track. They can stay here indefinitely, but if the mixing is not so efficient, and they can actually start to come down, lose mass as they go along, because as their helium content is enhanced, and they gradually loses the envelope mass. So because the Eddington limit is reduced. So as we do these detailed Mesa models, and Xu Zhenghao had done many of these calculations to show that, in fact, you can get, under these conditions, you can get the star's mass to light ratio to be maintained at some value. So now, if I have a population of these stars, and then these stars can heat the disk. So here is a heating factor. Here is a standard viscous heating. Now we introduce the stellar heating, and if they can evolve off the main sequence, they can produce supernova, and they can generate supernova. If they produce remnants, they can actually accrete power further. You get further flux. And if they re-radiate, as those people who are interested in protostellar disk realize that the outer region of this is often heated by radiation from the center, and you can get all of these as the source of heating. And the cooling is, you can also determine from well-known accretion disk theory, and you balance this to give you thermal equilibrium, and so you can actually see which is the dominant term. The dominant turns out in this region is the stellar heating. So the stellar heating depends on the luminosity of the individual stars and the surface density of these stars. And we can work out these quantities. If they evolve in this some manner on this time scale, you can work out the star formation rate. Okay, so you can go through all of this process in very rigorously, and not just hand-waving, give a model. So, but the power of the individual stars is determined by the conversion rate of hydrogen into helium. And this conversion is through one process on the main sequence, CNO cycle. And in CNO cycle, you don't generate additional alpha elements, but you enhance the helium content, hydrogen into helium, and you enhance the nitrogen over oxygen ratio. This is an important factor. We'll come to it. So in this unconventional stellar evolution model, and which is actually done with appropriate stellar evolution code, and you can actually determine a mass function. And this mass function is not an initial mass function. It's an equilibrium mass function. It's an equilibrium mass function because the nuclear burning process, the efficiency, the contamination of the helium content, and the change in the mass to light ratio is all determined. Okay, and furthermore, the star formation efficiency here is also not an assumed quantity, because it is required that this luminosity, the total luminosity of the stars, matches with the cooling rate of the disk. So in this unconventional star formation theory, and everything is determined. So now, how do we find observational evidence? So if the stars are heated by hotspots, and they ought to produce columns in their neighborhood, like in Saturn's rings, we see these columns. And especially in this disk, if you have hotspot, you can create local anticyclones, and you can show how the structure may change here. And so you have a column here, and if you have these columns, then these columns can actually reflect the light from the central source. Okay, so if you have a central source, and that is near the supermassive black hole, and it shines on a column, it is like the storm, these cumulative clouds. You see all of a sudden very bright. The clouds themselves are not irradiating, but you're shining on this region. And we can determine all of this because we're using reverberation map to probe AGNs that goes up and down. And so if they go up and down, you can actually see features in these disks. And through reverberation map, it's really just from the light echo. And you can actually measure this also in the line width, the detail line width, as a function of time, because these hotspots undergo revolutions around the central massive black hole. So therefore, you can determine these structures. And this is analysis that's underway. But when we look at the broadline region, we see enormous amount of information from AGN. And their spectral lines are so exquisite with information, many lines. This is a system that's redshift 10, and you see all of these heavy element lines. Now, some of this line, the strength of these lines may be due to the UV flux, and that determines the population, electron density population at different atomic levels. Some of it is due to metallicity. So how do you separate what you can attribute as metallicity, what you can attribute as emission line physics? You can look at some of these line ratios and you can compare them, because some of the lines you can pick will have the same electron excitation level, and from that we can measure heavy elements. So the broadline region, how is it produced? And you can see the line has width a few thousand kilometers per second. How it's produced is possibly because in this part of the disk, and this is where what planetary people who are interested in planets will refer to as a snow line, or the nettle grain line. These are regions where the temperature becomes sufficiently cool that the grains condense. When the grain condense, their opacity increases by a factor of a few to a few tenths. As a result, the Eddington limit becomes much reduced, so the radiation pressure has a much stronger influence in pushing the material up, lifting it up above the disk, and then they recondense. And so in this region, you have the interaction of the radiation here and with this marginally condensable gas with a combination of gas and dust. You can probably see all of the analogies with protostellar disk. Okay. So now we look at the broadline region. Broadline region is typically about 1,000 Rg, Rg being gravitational radius. So if it's 10 to the 8 solar mass black hole, 1 Rg is 1 AU. Okay, so there's also these lines which are called narrow lines, and they're further out, and maybe 10 to 100 times further out. And so we can go start to measure these abundance. The first thing you notice that the abundance you can determine here is at redshift, the abundance you determine here for the broadline region is typically 3 to 10 times that of the sun at arbitrarily large redshift, including 10. And so there's supersolar right away. That's the first thing you can see. Second thing you can see is that the narrow line region and the broadline region differs in metallicity. The narrow line region seems to be more suppressed, which tells you perhaps some pollution has been taken place between the narrow line region and broadline region. So material all flows towards the supermassive black hole, so that tells you that in this region that heavy elements are being produced. You can then calculate how many stars you need to do this kind of generation, heavy element generation, and you can compare it with the luminosity that's needed to achieve thermal equilibrium, and they match. Third, you can notice that the iron to hydrogen ratio, that's much more difficult to measure, but if you can measure it, seems to be subsolar. Compare the iron to alpha element ratio, that seems to be subsolar. And Eva would be able to tell you that's an indication of type 2 supernova, but not type 1a. So how do we put all of this together? Let's first look at this stellar evolution in these stars in the AGN disk, and here's the main sequence, post-main sequence, and then you can also look at the carbon ignition, and then pre-collapse, and then you can see where the yield comes out, in which region that you can convert oxygen and carbon into mostly oxygen into nitrogen, and if you're on this eternal immortal star track, and then you generate a lot more nitrogen. And if you can evolve up here, you can generate more alpha elements. And if you want to look at the more exotic elements, we're starting to do explosive stellar evolution. Now, I mentioned that these high metallicity are found in very high redshift as well as nearby. And when you do this measurement as function of redshift for different groups, there's systematic difference between different groups. But when you measure it and you find that if for a given group that there's little dependence on the redshift. Now this is completely contrary to what you are used to be told about chemical evolution of galaxies. At high redshift, the metallicity should be low, and how come in this context that the metallicity is high and is independent of redshift? The reason for that is because you're polluting it around the black hole, around the accretion disk, around the black hole, and this accretion disk continue to flow towards the central mass supermassive black hole. So the heavy element pollution that you generate here does not accumulate. So as a result, this is a saturation value, not an accumulative value. We can continue to look at these signs of metabolic stars. And when we look at it, as I mentioned, that the iron to alpha ratios you can see in these measurements, we can determine in this context. I won't bother to talk about the supernova, except to show that during the final collapse and the formation of disk around the supernova provides a release of gravitational energy, and that creates a shell. And this is kind of model that's similar to what people would see in terms of gamma ray bursts. Okay, so if we do this with metamorphic stars, we continuously form stars and return back a lot of yields, but we also return back stellar mass black holes. So as a result, the gas content will gradually deplete. So, and different models we can actually show as a function of radius into the central mass how this depletion can take place. If there are plenty of black holes inside this disk, you will gradually drain out the entire disk before they can come into here. Okay, it's a little bit like the Rhine River, and if you take out all of the water near Heidelberg, nothing will go into the sea in Holland. So, so this is the kind of drainage, and maybe this is the drainage that switched off AGNs and give you a time scale of the duty cycle of order a few times 10 to the 8 years. Now, the next stage I want to talk about is that when you work out, there's so many stars that can be produced, and in here, in fact, we can already see the number of stars in terms of the stellar density, the number of stars here, and we can already work out a stellar population here. Then this is starting to become a planet formation problem. Because when we have so many planetesimals in this environment, then these planetesimals will collide and they will merge and they become bigger. Now, the stars can do the same, and they would also have a possibility of colliding. I even use the Safonov number, which was developed for planet formation, to give you an indication the collision rate and the collisional time scales, and they may actually merge. So what is the consequence of them merging? And so let me show you some of these simulations done by Shi Yanlong, and showing you that these massive stars, and they're probably, well, they're dominated by radiation pressure for one thing, and so they're more likely to be approximated by gamma equals 3 polar-12, which is marginally stable, and when they do collide, and you can see there could be a lot of mass loss from this this plot, and in terms of density. And here is a plot of their chemical composition. So if you have two stars that has inside in the interior, you may have a helium concentrated interior, and that collides with a more massive star, and that would enable the mixing of these two different materials. So mixing becomes a very efficient process if they can collide. So you may recall that I said before that if you mix, then what happens is that you will start to resupply, replenish hydrogen in the core region. And so this is like a helium content after you go through a merging process, and you have the mass slightly increase, but the average helium content gets reduced, so you get a little bit more extended lifespan. And if the collisions occur frequently, and then you can have indefinite immortality. Even beyond that, when in certain regions of the disk, that the time scale for capture and collision is so short compared to the mass loss rate, you may even have runaway accretion to form very massive stars. Okay, so this is a consequence, and that how it would affect the stars. And as you can see, that there are new stars being formed in one track. If there are relatively few of them, they just evolve without mixing, they will become immortal stars. Without mixing, they will become the standard metamorphic stars. With mixing, they will become the immortal stars. But because there's a possibility for them to collide and they undergo mixing, I can actually have a prolonged lifespan. So the strange thing about these stars is that they may have 300 solar masses. They can live for 10 to the 8 or even more years. Very unconventional. Okay, so let me move on a little bit more. So I said that the collision enables the evolution towards an immortal track, and along these tracks, you tend to generate primarily generate helium and nitrogen, and you actually deplete carbon and oxygen, but the alpha element content is conserved. Whereas when you do this, you get enhancement all the way. Can we use observation to test this idea? So let's look at observation again. This observation of reverberation map tells you that the central black hole goes up and down in luminosity, and it shines into different regions of the disk with some time delay. And so when it's very bright, it can actually reach out to much larger distance. When it's not so bright, it reaches closer distance. So if we can go into the emission line and at the very bright stage versus faint stage, we can actually get a reverberation map to tell us the difference in metallicity from an extended region of accretion disk around supermassive black holes. And here is a set of analysis and being carried out for some of these different lines at different stages. This is done by a graduate student, Jiamu Huang. And from here, we can start to determine things like whether there's any gradient in the context of looking at nitrogen features inferred from various line ratios, and we can also try to extract the evolution. This is evolution of nitrogen, and this is evolution of CNO. So the upshot of this preliminary determination is that we actually see that this is in the broad line region, and as you can see, that the nitrogen and slope, this is the nitrogen slope goes down like this, and C plus N plus O is essentially flat. And you can combine this with a diffusion calculation. You basically say, okay, which means what is happening is out here. Actually, I have a cartoon in the next slide. What is happening here is that in this region, we have metamorphic star, and that generates heavy elements, including C plus N plus O, as well as iron. And they don't collide very frequently because their surface density is low. And so they generate the heavy element. Black holes are produced in this region. But the region that's closer in this broad line region, and then what happens is that they frequently collide, and mixing becomes efficient, and then they prolong their life to become immortal stars, and they convert hydrogen into helium, nitrogen gets enhanced, and the CNO remains the same. So this is kind of schematic drawing that you will have here, and that matches with what is observed from this kind of diagram. So these are preliminary inference as evidence of immortal stars may be present in this region. For those who are, I draw a lot of analogies between planet formation and AGN disk. And one of the most interesting aspects of planetary disk is the formation of these gap structure and the presence of protoplanetary embryos. And does it happen also in AGN disk? Yes, it does. However, it is not like the typical type of structure that you see in protostellar disk, because the presence very often of very strong turbulence, gravitational turbulence, and which can generate with strong turbulence, so the wake can actually get very distorted and stochastic. You get stochastic migration, sometime in, sometime out, and you can actually change this flow pattern. Moreover, there are many of these stars, and their wake interfere with each other, so the diffusion, so the migration is actually a diffusion rather than systematic change of location from outside towards the center. Nevertheless, some of these stars may be able to get close, sufficiently close to the inner boundary of the accretion disk, which is known as ISCO, inner stable orbit, last stable orbit. In this region, that you can actually have very strong tidal effect imposed by the supermassive black hole on the migrating stars. And under these conditions, you can generate a different type of tidal disruption event, and that will cause inflation and tidal disruption, very different from the standard tidal disruption event from flying stars on parabolic orbits to give you this tidal disruption. And one can predict the signatures and the light curves, and there are some TDEs in slow rising TDEs is being observed, and by the Zwicky transit factory. So here, let me put in with a simulation of few hundred embedded stars, and they interact with the disk. And now, these type of simulations all require some degree of idealization, because no simulation can have sufficient resolution, can run sufficiently long to capture all of the physics. That's what's going on. So you can see all the interfering, the tidal wake, and you can see the growth of relatively massive objects. Okay. So now let me mention that some of these tidal disruption events, I misplaced this. The tidal disruption events, when they undergo tidal disruption, you can form this type of structure, very much like what some people are suggesting for WASP-12b. So I talked about star colliding with stars, but I also talked about stars can generate black holes. I also talked about stars can move around. So what happens, you have the coexisting of stars and black hole, and the black hole population keep on going up, and there's a possibility that the black hole may collide with stars. So if a black hole collides with a star, goes inside the star, what happened to the star? So I'm going to look at two consequences. One is a single black hole goes into the star, and what does it affect? How does it affect the massive star? And second is that a second black hole comes in, and how does it interact with the supermassive, with the already embedded star? Okay, so here is an embodied simulation that is done by Wang Long, and try to capture the stellar merger rate and the black hole capture rate, and then we try to go to the next step. Okay, now, and try to understand that if you capture one single star, what happens? And these stars will undergo very quick in-spiral, because the density inside the star is more than 1 gram per cc, and when it gets into the interior of the star, very quickly it would undergo rapid in-spiral, Let me see if I can show this. And you can go rapid in spiral, get to the center, and there are several effects that's taking place. One is that it will mix. It will quickly mix the content in the core with the content in the envelope. Another way to bring back hydrogen into the core and to rejuvenate. Second, it could inject so much internal energy from the frictional heating that part of the star envelope can be lost. But in general, the black hole, if it's small in mass compared to the massive stars, like a few solar mass versus few hundred solar mass, the envelope's mass loss is not significant. However, if the massive black hole enters into the star has comparable mass, then the energy release will be sufficiently large to actually get rid of all of the envelope. And this may have consequences on the black hole mass function. And the other thing is, when it gets to the center, you will say, oh, it's like there's a bug that goes into the central gut of the star, and the star would really become very violently reacting to it. But actually not, because the black hole goes into the center, although it can accrete to produce energy, but that energy is limited by Eddington. The nuclear energy generation inside the massive star is also limited by Eddington. And that tells you that the ratio of energy generation from the star due to nuclear energy generation compared to the black hole accretion, and the ratio is the mass ratio between the two, the core and the black hole. In general, it wouldn't affect the internal structure very much. Okay, so it can, if your single black hole, low mass black hole, goes in there, it can sit right in the middle. Of course, more massive black hole, it would do major damage to the stellar structure. Okay, so now if it gets into the center of the star, there's a convective core. So the cores, this convective motion tells you the material that you're accreting is changing in spin orientation at all time. So the accreted mass will actually increase the mass of the black hole, but the accreted material will actually decrease the spin because it randomizes the spin. And this will have implications in gravitational wave merging event. Okay. So now I have one inside here. I'm going to put in a second black hole into this region. What happens? This is work done by Hu Qingru, and that if you go through here, okay, you feel this is the size of the star. Very quickly, there is a black hole already in the middle, and then they very quickly in spiral towards the center, form. This is just a blow up of here, and this is a blow up of here, and then you form very tight binary. The binary, this time scale is less than 1 day. Okay, so you can actually get this capture occurring into here, but eventually it gets into a binary that is relatively close. The stellar envelope has little influence on frictional breaking. So, and at that point, from that point onwards, and you rely on gravitational radiation to bring the two black holes closer in, further closer in, on the time scale of a few thousand years. So you can do this with embodied type of simulation. Here is with hydro simulation, and then you can see that here is a star that went into a black hole that went inside the star, and this is the mixing it will cause, and then eventually it will merge. So there's a possibility of this merger event that tells you immediately this is linked to maybe this is one particular channel that could provide a source for the LIGO events, you can work out once it becomes gravitationally dominated by gravitational radiation, the rate of change, the semi-major axis, eccentricity, and the rest of it. Okay, so you can work out this probability, and we can work out from the mass function of the stellar mass function, black hole mass function, and the AGNs luminosity function, we can actually start to determine a population of the system. So is there a way to find an electromagnetic counterpart to all of this process? So if a black hole merges in the center, the merging product will have a recoil velocity because the gravitational radiation at the last stage is not isotropic. So it will have a recoil, but the velocity is not big enough to escape from the envelope of the star, and it goes up out here, and then it resettles into the middle. And during that process, you can actually produce a lot of frictional heating. Okay, so you can see in here, there is this one escape, but now we do a more realistic case here, and you'll see that this goes out a bit, and then it causes the star to expand. If the star expands and it reflects the radiation from the central source, and you can actually see the shine, the reflection into here, and that may be one way to find the electromagnetic counterpart of these gravitational wave events. Okay, so I described how accretion of gas can determine things like spin angular momentum. So you can then compare it with the chi-effective distribution of the LIGO events. And here is the mass function that you can determine from this type of events. And you can do this all into your stellar population in this environment, and then try to determine likewise the kind of distribution that you can find. Okay, so now I hear this, I like history, and one of the last presidents had made this remark that ask not what you can do for what your country can do for you, but ask what you can do for your country, and you just convert a little bit and ask not what your AGN can do for LIGO, ask what LIGO can do for AGN. Okay, so and then from these LIGO events, if they're in the presence, if they're in the deep gravitational potential of the host stars, and then these Turing event, the evolution of the wave function will be different. And so we're currently trying to determine what happens there. Okay, so it brings me to sheer speculation, from speculation to speculation. Now, here we see populations of little red dots. And it's the hottest topic, and because people say, oh, they're too compact, they're not resolved, they're very luminous, and maybe and they have all this V-shaped spectra. But what you don't find is that so one of the questions is, are these primordial black hole? The argument for primordial black hole is that maybe when you look at these spectra of these black holes, and when you look very closely at the spectra of black holes, you see those mostly hydrogen and helium, but you hardly see any alpha elements. It's about at the -2 level, solar value, and you don't see dust. So these are very different from standard AGN. So one argument is that these are the first population of black holes that got there. Now, what I described to you in terms of immortal stars, they don't produce alpha elements, and they don't produce iron if you get them onto this stage. So is it possible that they are indeed super dense nuclear clusters, and that collision between the stars are so frequent that you can evolve them in this way and turn into many, many immortal stars, and that release very little heavy elements, alpha elements, but nevertheless enough alpha elements to power the CNO cycle and to enhance nitrogen enhancement, and which is observed. And furthermore, is this a mechanism that I can use stars, massive stars, as a carrier of black holes and to the neighborhood of very dense region, and eventually causing them to actually undergo merging event without worrying about the Eddington limit? So we try to do this with various simulations, and including stellar evolution and stellar dynamics, and try to do the appropriate analysis in this context, and see whether there's a possibility that you can rapidly grow the central massive black hole by moving, capturing, and migrating, and then bring clusters of small black hole into high concentration without the barrier of Eddington limit. I'm almost done. So here's my take-home message. I think there are many messages here in terms of LIGO event. It tells you that the LIGO event is most likely to be associated with metal-rich AGNs, and the origin of metal in AGN. I provided you with a scenario, and that needs to be further explored and proved, because many of the concepts I introduced are out-of-the-box concepts, and so there are details that still need to be probed. But I would really like you to take away this message, that AGN disk resembles in glory details to protoplanetary disk, and many of the processes that you observe that I described today can be applied to both contexts. In fact, I even tried to do this with my host the last few days when I was in the Swiss Alps, and I was trying to convince Michel Mayor, and he says, "Oh, there's no problem. There's already a science popular book translated into many languages, including Chinese." So he showed me this, that Michel Mayor is being pulled out of a black hole. On that note, I thank you.
Thank you for this talk. I'll open the floor to questions, especially from students and postdocs to start.
Thank you for the inspiring talk. So speaking of the potential observational evidence of these stars, you mentioned the reverberation mapping technique. I was wondering if it's possible to have some more direct ways, like the, I don't know, VLT gravity plus. Would it be possible to observe something more direct?
I didn't quite capture everything you said. You wanted to know other observational evidence based on some other method. What was it?
Yeah, the VLT gravity plus instrument, for example.
Yes, okay. So from the VLT gravity observations, we are trying to get to in two different approaches. One is that eventually they will quite, in the near future, they can resolve some nearby AGNs. And we can produce some signatures that give you the luminosity profile of AGN disk. This is not the same as the standard AGN disk because you have so many stars in the outer region that generates the nuclear energy to power the AGN luminosity profile to give you equilibrium. So we can produce those, and we can produce things like these very uneven, non-smooth surface. But more importantly, I think when you go back to gravity experiment, especially with the central region of the Milky Way, and there's so much more to tap out, and there's an enormous amount of information you can get by looking at these consequences. For example, if you form a generation of these stars, they will influence the orbit, the trajectory of these stars relative to the central mass, okay? Because they can perturb these orbits. And is that perturbation, is that the reason why the old star's stellar distribution actually bends down from the standard Bacall-Wolf distribution? Okay, so these are dynamics that we're trying to explore further, and we will benefit greatly from gravity experiment.
More questions?
Hi. Before I ask my question, can you go to, I think, slide 31?
Go on.
I apologize if
No
not.
worries. No worries. There.
Yeah, okay, I think, yeah, that works. So for the mass that continues growing for the rejuvenating stars, at least I'm pretty sure this graph would indicate that also the hydrogen mass fraction in the core is jumping very sharply.
Yes. Very good. You were talking about this, I think. This one, right?
Yes, that too.
Yeah, right here. Okay.
So my question is, do you know how the mixing time scale in the stellar internal structure relates to the merging time scale, in the sense that are the cores already starting to rejuvenate before merging with the other core?
Yes.
Okay.
Very good. Very good. That's a very good thought.
Do you then find that there's a dependence on the actual convection parameters in the star that affects the efficiency of rejuvenation? And will that affect the rates of runaway mergers we expect to find?
Okay. So first of all, if you do it alone without merging, okay, and we examine very carefully about the effect of convection in mixing in the core, and then in the radiative region, there are various other processes, meridian circulation, and the magnetic instability. And what we find is that standalone stars are unlikely to become immortal. Okay, and so now when you have this merger, and on dynamical time scale, very short, and then they get reshuffled. Okay, but then on the thermal time scale, some of the envelope readjusts, because now, as you said, that the helium content, hydrogen content, helium content, and other element content gets all shuffled. And then they need to go make adjustment in terms of nuclear energy generation, in terms of heat transport. That's longer time. That's thousands of years. These are very massive stars. Okay, and then you go through that, and you compare it with merging time. The merging time at different locations is different. There are locations where the merging time is very short, and those are the locations where before you can even establish thermal equilibrium, you already gobbled up by somebody else. So that's the runaway location. So so all of these very rich possibilities can be determined, and we're trying to do a very systematic recipe. And you say, this recipe gives you this, that, the other. So all of the range of possibility at this moment still exists. It's just a boundary condition.
Okay, that makes sense. Thank you.
Oh, I should have used the cube. Okay. Let me get all the way over here, Ralph.
Thanks, Doug, for this tour de force through the similarities between protoplanetary and AGN accretion disks. I would like to follow up on your stellar collision model. I think there is a much easier pathway, right? Because
You're absolutely right, and I think we are tried to do with various initial prescriptions, and there are many complicated things. So we thought maybe we should try polysopes, and because it's radiation pressure dominant, and it is sensitive. That when you have n equals 3 polytrope, as you know, it's marginally stable or unstable, and you can actually lose a lot of mass. But I think the detail may not be so important.
maybe we should take this offline. I think the concern with your model then is once your collision rate drops to a larger cadence or larger time scales than the Kelvin-Helmholtz contraction phase, the thing will just collapse to a black hole. And I talk about stars that have accreted, let's say, a few hundred solar masses, right?
Mm-hmm.
And then none of these immortal star business or whatever you call it.
Yes, metamorphic.
Metamorphic star is because the thing will just make an intermediate mass black hole and it's gone for your, rejuvenation pathway.
Right. So this is why I was saying I'm making comparisons between thermal timescale and collision frequency. Okay, and the possibility of direct collapse into a more massive system. Those are from runaway systems, and the collisions very frequent. Before you can adjust, and the actual internal structure is we still haven't yet had time to study for that runaway system. But it is an important process, I think, for the little red dots.
So one last question.
Thank you. Thank you for the great talk. If I understood correctly, one of the outcomes would be nitrogen enhancement, right?
Yes.
So one interesting observation that people have made for the bulge of the Milky Way is that there are quite a few stars that are nitrogen enhanced.
Yes.
Could there be, in principle, any relation to these early phases when the Milky Way was an AGN and that maybe some pollution with nitrogen happened due to the effects that you described, which might have ended up in a subset of stars?
Yes. It is on our shopping list. Try to address the issue of the rapid enhancement of nitrogen in high redshift galaxies. Now, the problem is that at this moment, I think I know what to do with AGNs. because there's a central supermassive black hole, and I can work out the boundary condition. Now, I don't know so well the superstellar cluster environment and the galactic environment, try to infer, but it's under our radar screen, and we would like to explore that. Thank you.
Right. So before we thank our speaker again, I'll just say there's dinner with the speaker, so you can talk to Hao Cheng if you are interested in joining. And again, thank you for this
Thank you.
interesting talk.
Thank you.